Hello everyone, this is Liz McCormick from Bryn Mawr College. Today we're going to look at a problem that involves motion in two dimensions, and in particular in the case where the motion is due to a force that results in a constant acceleration. One of the most ubiquitous examples of this is called projectile motion. And this is the motion of an object under the force of gravity, where the acceleration of the object is just the little g constant of minus 9.8 meters per second. The scenario we have here is an arrow is fired horizontally at 40 meters per second. "40 meters per second is the initial velocity of the arrow. In this problem, it will travel 20 meters in the horizontal direction. And the question we have is, from what height was it originally fired? So I've got a diagram here that kind of maps out the motion of this object, the arrow. And what I want to highlight here is, in this example of two-dimensional motion, we can understand it as undertaking a path on a coordinate system of x and y, where y obviously can represent the height, and x can represent the range over which it travels. The green line here is this quadratic pathway. That is, it's the trajectory of the object, and with this kind of motion, it follows a quadratic function. I've written in red an indication of the velocity of the arrow as it flies through the air, and you see it falls to the ground because of the action of gravity pulling it down. And I'll just remind us that gravity is minus 9.8 meters per second squared. I'm using a shorthand. I should really say the acceleration due to gravity is this quantity. And because of that acceleration, our object is falling more and more rapidly towards the ground as it moves in the x direction. The other important thing to keep in mind is, because there's no acceleration in the x direction, that initial velocity in the x direction will remain constant throughout the motion. It's the velocity in the downward direction that's getting bigger and bigger larger and larger as the arrow flies through the air. And it's this component that's growing that causes it, that's part of its falling to the ground. So the quantity we know is the velocity and the range. This is the initial velocity v naught. We see that it's initially in the x direction, and we know the range here is 20 meters. So an important thing we're going to remember is we can actually model the position of the arrow as it flies through its path in terms of this vector r, which is called the position vector. And here we've got it written out so we can see it. Now, this is interesting to kind of remember what a position vector is. It's usually with respect to some origin. So what this position vector is describing is this vector throughout the motion of the arrow. This is the vector r. And you can see, of course, it's going to be a function of time, and it's going to depend on the initial position, the initial velocity, and the acceleration. In this case, this is the acceleration due to gravity. And as more time passes, you plug in, time is the parameter here. For a given time, you can actually now solve for what this vector is, pointing to the position of the falling arrow. And many two-dimensional problems benefit from the idea that we can treat the motion in these two orthogonal directions as independent motions with their own independent relationship. So, for example, if we write our vector r in terms of its components in the x and the y direction, and here I'm using I hat to indicate the x direction and j hat as a unit vector in the y direction, we can then write equations for the x and y position of the falling arrow in terms of the x and y components of the original position vector, the original velocity vector, and the gravity vector. I should say the acceleration vector. And that's what these equations end up being. We have the x position is going to be, in general, be given by its initial position, its initial velocity in that direction, and the acceleration in that direction. And similarly for the y coordinate, its initial coordinate, its velocity in the y direction, and its acceleration in the y direction. So this is the general framework. Let's go ahead and apply it to our particular example here. I've redrawn our drawing of the motion and our original equations from the previous slide. We have here and here. And now what I'm going to do is establish what are the particular values in our problem. Well, you can see that the arrow, let's take the x-coordinate first. This is the position along the horizontal axis, and we can see that its position along the horizontal axis has an initial coordinate of 0, and then as it progresses, its velocity in the x direction is this initial velocity v0 as a function of time t, and its acceleration in the x direction, in this direction, is 0, so that term is 0. We look at the y-coordinate as a function of time. We are interested in knowing from what height it was originally launched, and what we're going to do is look at the scenario where y0 is something we want to know. We know that its initial velocity in the y direction is 0, it's all in the x direction, and we know that the acceleration is totally in the y direction, in the negative y direction, so we have this term. Now I've set the y-coordinate to 0 because I'm in particular interested in a particular time when the arrow has completed its full trajectory and its y-coordinate is now 0. So it's important to note that by putting this 0 in here, I'm actually considering a particular time t when that's the case. So let's see what happens when we put in the original height from which to fire the arrow. Our numbers for this problem. I've again moved the equations from the first page here just to repeat them. And if we go from this equation, we can easily see that this translates to x equal to v0 times t. And this one here translates to y0 equal to plus 1/2 gt squared. And if we go up here, we solve for t, we get this equation. And I've moved this one right here to get this second equation, putting in the value for t. So this is our final result. We'll be able to find the initial height from which the arrow was fired in terms of the final range x and the initial velocity v naught. So here we can go down here and plug in those numbers. 1/2, 9.8 meters per second squared, 20 meters over 40 meters per second, the whole quantity squared. And then I can quickly estimate this as being roughly 10 over 2, this being roughly 1/2 squared, and then it gives me 1/4 times 2 gives me 8, it's roughly 10 over 8, and that's roughly 1.2 meters. Now the final thing I can do is check out our units. So we have meters per second squared from here, and then we have meters squared per second squared here, and lo and behold, these second squares cross out, these meter squares cross out, leaving only 1 meter, and that's of course what's represented there. So there you have it. We've got our answer, 1.2 meters, and we could do kind of a mental check. That's not so bad. In fact, if you were an archer and you were firing when's the last time you actually took archery class? But 1.2 meters is not an unreasonable height from which. The final thing I wanted to make before we conclude this video is there are several places in this calculation where you've had to use some math skills. And depending on how comfortable you were, there's an opportunity to go and practice, refresh, kind of remind yourself about those math skills. Now, what were they? First, we definitely were understanding the trajectory of the arrow in terms of a position vector. So if that part where we went into using unit vectors or vector components, if that was a little rusty for you, you could easily go do the module on vectors. Another math skill we used involved being able to rearrange formulas and to solve equations. If any of those areas seemed a little bit confusing or took you a little bit to follow, you can review those modules too to kind of refresh those skills. And finally, at the end there, we took a look at the reasonableness of the solution, and we looked at the units of the solution, and we're able to kind of work with those ratios and proportions and unit conversions, which is another area of math that was represented in this physics problem. I am having trouble writing and speaking at the same time. I appreciate your patience. I'm going to be doing a lot more practice on these. Conversions. Well, that's it for this video. I hope you found it helpful, and I hope you will indeed take a look at any of the math modules that you want to do some practice with, and come on back and try a similar problem all on your own.